Section 22.6 Phosphines. The phosphinol ligands are also strong-field ligands. They behave like the carbonyl ligand because phosphinol ligands are both sigma donors and pi acceptors. So if you look at this structure, this phosphine has two lone pair electrons that can be donated to the metal to form a sigma bond. At the same time, there are empty orbitals on the phosphor atom. For example, the PR sigma star antibonding orbital that can accept electrons from the metal. Phosphorus also has 3d orbitals, empty 3d orbitals, that can accept electrons from the 3d orbitals of the transition metal. So again, this phosphinol ligand is both a sigma donor and a pi acceptor. It's a better sigma donor than carbonyl. It's a weaker pi acceptor than carbonyl. I'm going to explain why this is a weaker pi acceptor. This is because this phosphinol ligand may accept electrons from the transition metal in two different ways. One is to use the sigma star antibonding orbital to accept the electrons. The other way is to use the empty 3d orbitals to accept the electrons from the transition metal. But this sigma star does not align well with the 3d orbitals on the transition metal. I think the angle over here between this PR antibonding orbital and the bond axis between phosphorus and the metal is 109.5 degrees, approximately that. And it's not a perfect 90 degrees. And now if we look at the empty 3d orbitals on the phosphorus, well, they have much higher energy than the occupied 3d orbitals centered on the transition metal. So when two orbitals have very different energies, well, the interaction between these two orbitals is minimal. In that case, the pi backbonding is weaker and often much weaker than in this transition metal carbonyl complex. However, because this phosphinol ligand is a really good sigma donor, so overall, this phosphinol ligands are also strong-field ligands. Now let's look at the bonding in this picture. So over here, this phosphorus has lone pair electrons that can be used to form the sigma bond between the metal and this phosphorus. This is simple. This is a really strong sigma bond, stronger than the sigma bond between transition metal and carbonyl, because phosphorus is okay to give away electrons. It's more willing to give away electrons than this carbonyl ligand. And now let's look at pi back bonding. So there are empty d orbitals, 5 of them centered on phosphorus, completely empty. So they are ready to accept electrons from the metal. So now you can see the overlap between the occupied 3d orbital centered on the metal and the 3d orbital centered on the phosphorus. Of course, you need to use the orbitals with the right symmetry so that they can match. All right, constructed interference. And then this metal can donate 2d electrons back to phosphorus via pi back bonding. But this is typically a weak pi bond. Again, this is because the energy of the empty 3d orbitals on phosphorus is usually much higher than the 3d on the metal. So there's not much interaction between this d orbital and this d orbital. So we can somehow make this p a better pi acceptor, but then the sigma bond will be weaker. I'll talk about this. So over here, this p is bonded to 3 R functional groups, and we can design the structure here by changing the ligands. So when these R functional groups are electron pushing groups, for example, methyl groups, cyclohexyl groups, and then this PR3 can become a good sigma donor due to this electron pushing functional groups. But then at the same time, the phosphorus will become a poorer pi acceptor. And also, we can change this ligands, the 3R ligands, to electron withdrawing functional groups. And then in that case, this PR3 becomes a poorer sigma donor, but a better pi acceptor. So if you use PF3, and then it's going to be a good pi acceptor. The fluorine atoms are electron withdrawing atoms, and they help lower the energy of the empty 3d orbital centered on phosphorus. So those empty d orbitals on phosphorus are more welcoming, are more ready to accept the d electrons from the metal. So they become a good pi acceptor. So overall, it's very difficult to design the functional groups to strengthen this phosphorus metal bond, because either you have a good sigma donor but a poor pi acceptor, or you have a poor sigma donor or a good pi acceptor. Except this, if you know your transition metal atom is electron poor, all right, and then, well, you can just use electron pushing groups here to help strengthen the sigma bond. If your transition metal is electron rich, just many d electrons, and then you can use the electron withdrawing groups, 3 of them, to be bonded to phosphorus, such as this PF3, to accept the d electrons from the transition metal. And in this way, you will have a really strong pi bond between the metal and phosphorus.